coming all the way from just next to Marbella on the Costa del Sol. You'll be delighted to hear it's chucking it down with rain today, and made me feel, well, a little bit homesick, to be honest. But what I hope you can see is that I've posted a link in the chat, and that should be a link to this presentation. So just in the very, very slight chance that there's some sort of technical hitch, then you can always access that presentation through the link. It does take you to my website, where all of my presentations have been posted in the past. I wasn't planning on monitoring the chat too closely during this session, but if you do have any questions, please do pop them in the chat, and if we can tackle them as we go, we will. Otherwise, there'll be some time for questions at the end. So without further ado, I think we should get underway. And as you heard, my name is Stuart Welsh, and there's been a lot of changes in my life recently. One of them is leaving Scotland, of course, moving to Spain, and working here in an international school, which has been fantastic, a great opportunity. And all that changed again last week, where I took up a new role working with LaSalle Education, who you might be familiar with. I'm working now full-time for LaSalle as a maths educator. I'm still living here in Spain and working here in Spain. So that's why we've got the corporate slide deck today. You can see the branding, but don't worry, I'm not going to try and sell you anything at all. It's same old me, just running through some of my thoughts on, in this case, solving equations, and in particular, teaching for understanding. So if we can get going. As you heard, you know, my name's Stuart Welsh. You can get me on Twitter at Maths180. It would be wonderful to hear from you and to hear your thoughts on today's conference. And I've been teaching for over 16 years now, teaching maths for over 16 years. A majority of that in Glasgow, at the High School of Glasgow, where I was head of maths and also research lead in that school before moving out here to Spain. So I'm just going to close my camera just now so you aren't distracted, and we'll get on with the presentation. So the first thing I thought we should talk about is, why have I decided to put together a session on solving equations? Because we really need to always ask ourselves, are we trying to fix a problem that doesn't really exist? And I think the honest answer is that actually students generally do quite well with routine equation solving. It's something that they tend to pick up, and that they can do most of the routine questions without too many problems. But I started to wonder more and more over the years whether they see equation solving really just as a set of rules and procedures, almost moves to be made. Now, you could argue that solving equations is a set of rules, procedures and moves to be made, but I feel there's a bigger picture here, a more of a conceptual understanding of what it actually means to work with, to manipulate and to solve an equation through. And so I've been thinking about different ways to try and connect up the various representations that we can use when it comes to equations, building equations. And I'm hoping to share some of that stuff with you today to try and get beyond just a set of steps. Solving an equation is more than just the sum of its constituent parts. I agree that we might be doing something like add 5 and then divide by 3. Those are the two at the most basic steps, but ultimately solving an equation is a bigger thing, and we want to try and help students understand that, because if they can conceptualize this thing, then they'll have more success with harder equations further down the line. So why this topic? Well, there's an equation, and I'm sure if you look at that, you might in your mind be able to imagine what might go wrong here when a student was trying to solve this. Now, the common mistake here is really not understanding the order of operations, and perhaps you might see the next line of working looking like this. So what's happened here is the students understood that divide by 2 requires some sort of multiplication by 2, but hasn't fully appreciated that both sides of the equation need to be multiplied by 2. And I think these are the sort of mistakes that start to creep in to some students' work, and I think we can avoid those. Here's another one, perhaps a little bit to do with solving equations, also just to do with basic number work. What do you think the mistake could be here? And so what we want them students to be thinking here is we're going to divide both sides by 8, but of course they'll see 8 and 4, and you might well end up with something like this. Yeah, well done, Michael, in the chat there, good job. And so here's another one, this time with the unknowns on both sides, and it's not always going to happen, but this is the sort of thing that can happen. That subtract x just sort of joins with the 5x, and suddenly we've got 5x minus x gives us 4x. It's not always what's going to happen, but it is a common type of mistake that creeps in. And then of course this is a horror show sometimes. What might be the problem here? Well, have a think for a second. So I would wager that you might be getting the answer of x equals 5 or x equals minus 5 even, and that's the issue really, is that negative x. In fact, I would go as far as to say some pupils will read this as 3 minus and then combine that with the 8. So they're actually reading 3 minus 8 in this, which is where you might get the 5 or the negative 5 from. In just about every case when this goes wrong, the negative that's in front of that x there disappears. So we want to try and look for ways to sort of avoid that sort of situation. Here's another one, of course. Whenever x is on the denominator, we can expect a world of wonderful responses. And so we might see something like this. Obviously, the 3x can just float up to the numerator there. There's no problem with that. And maybe 5 will multiply by the 2, or maybe you might see the 5 then divides the 2. But quite often that 3x ends up losing its position in the denominator and just sort of floating into the numerator there. So I think there's definitely a conversation to be had around some of these skills. This one in particular, I'll just maybe let you think for a moment what you might expect students to do next. Now, try and detangle in your head what you might do next with this equation from what you think students might do with this equation. But I would wager that most people are thinking, their students at least, and maybe most people as well would be doing something like this. Now, obviously that's not wrong, but you've got to really ask yourself why. Why would you expand those brackets in this case? Because if we take that same question again, and we appreciate that both sides of this equation divide by 3, then why wouldn't we just go to this on that stage? Now, I've seen textbooks where there are whole pages of questions involving equations with brackets, where every single one of them can be simplified in that first step in the way that I've done here, by dividing both sides by some term, by some number value. This is an exercise in a textbook on expanding brackets and then solving. But of course, you don't need to expand those brackets. So I would like my students to be able to spot that there's a common factor here, 3, that we can divide this down and simplify it. And again, those are the sort of things that I feel are missed if students start to sort of take equations as being procedural and see some brackets, just expand them, and don't take a second to stop and think, well, what does this equation mean when it's been presented to us? One of my personal favourites. So again, just imagine what might go wrong here. And of course, I'm sure we've all at some stage seen this. It would make perfect sense. Sine is beside the x there, must be multiplying. So of course, how do we undo sine? Well, we divide by sine, of course. And there we see a sort of lack of appreciation of inverse operations. And then just trying to link back to just basic multiplication there. So again, something that is important, and we'll talk about it more, is this idea of inverse operations. Another nice one. I mean, to be honest, there's a whole world of incorrect answers here. All sorts of great things might happen. None of them, of course, going to actually be correct. that sort of thing can cause all sorts of problems, even though it's not really that difficult an equation if we just have some idea of where it is that we're trying to go with this. And so we've definitely got scope to try and explore these sort of fundamental concepts, the reasons behind why we do what we do when we're solving equations, and hopefully some of that's going to come across today. Now, in my musings on this, I've come to the kind of conclusion that solving equations needs to be this sort of blend of these three key fields. I do believe that the best way to teach equations is through some sort of balance model, and the idea of equality is obviously so important to that. But going hand in hand is this understanding and use of inverse operations. And then, of course, the third part here to this diagram is actually the notation that we use, the formal and the abstract notation. So we're hopefully trying to build up strength in each of these regions so that we can eventually hit this sweet spot in the middle, the overlap there, the central region where everything comes together. So you might be starting to appreciate that this is not a simple topic. And I wrote an article in the latest SMC journal, and Carol Lyon, who very kindly gave me a bit of feedback as I was writing it, will also acknowledge that this is a really difficult topic, or I found it a really difficult topic to try and come up with the one overarching approach, because I just don't think there is one. I don't think there's a formula or a list of procedures that will just allow everybody to teach solving equations effectively. It's a really dynamic and changing environment where you need to be responsive, where we want to try and dip into different representations at different times, go to different difficulty levels when the students are ready. All of these things make this very, very challenging to get absolutely spot on, but I still think that there are ways that we can employ different strategies and, as I said, representations to give our students the best chance of forming the strongest conceptual image and conceptual model of what it is we're doing here. So if we take equality and balance, then I'm going to have a look at how we can use coloured rods, Cuisenaire rods, to try and build up the understanding behind equality and balance, but also some of the more formal notation. Then we can look at algebra tiles and see how they can be used. Again, they help building up on this idea of equality, working with balance and the notation. Function machines, number stories, that's something that can start to take our conversation towards inverse operations, and also connects up quite well with notation. And then the fourth thing hopefully we can have a look at today is scales, balances, and mobiles, and not mobile phones in this instance, as you'll see later on. So yeah, you can see we've started to build up a bit of a complex picture there. Now, I just wanted to pause for a moment and see if anybody had any questions or wanted to make any comments at this stage. I'm quite happy to take a pause here and there. And if you want me just to crack on, then just let me know in the chat window and I'll just push on. Wonderful, thank you. It's great to get the feedback. Now, I have been working in a school for the last year and a half. I only just stopped there, and while you've been on lockdown with schools closed, I've actually been in class teaching since September there. And so I've been doing a lot of face-to-face teaching, which is great, and I know that many people are very excited to get back to that. But I did do a long spell of online teaching as well, so I appreciate all the challenges and difficulties that brings with it. And so it's always good to get a little bit of feedback. Is really helpful in the chat. So Alan Duncan wants us to crack on, so I think we better crack on. Something that's definitely worth talking about are the prerequisites when we come to solving equations, and we need to appreciate, and I'm sure we do, that these will increase as our students move deeper and further into and through the curriculum. Essentials at the beginning, of course, are number bonds and multiplication facts. That could be a big barrier to solving equations if those aren't secure enough. So definitely important to build those and be secure with those. Order of operations is vital if we're going to talk about function machines and ultimately inverse operations. The order is going to be essential for us, so understanding the order of operations is critical. Negative fractions, that's where so many mistakes come from when we're solving equations. Usually careless mistakes, or what we call careless mistakes, although these are usually relatively simple procedures that have not been given enough attention by the student. So all of those, we know this, these are common mistakes, so if we can do what we can to build these prerequisites as strong as we can before going into working with equations, it will clear the path that we can focus really just on what we're doing with the equations. And then obviously simplifying terms, substituting into expressions, that sort of algebraic stuff is very important when we come to solving. So my sort of guiding principle here is always try and plan ahead. So think about the hardest equations that you're going to try to be teaching in this next unit, and then think about what are all the stumbling blocks, negatives, fractions, all of that sort of thing. Identify them, test them at the beginning, teach them if necessary, and hopefully we can have be starting on the topic of solving equations from a strong standpoint. Quick word on notation, and it's really just this idea that students will meet the equal sign long before they meet any formal algebra, and so a lot of them may well come to see the equal sign as like a command to perform some sort of operation. Seeing the equal sign as a command to do some sort of operation, like produce the answer, so to speak. And so we want to try and introduce this idea of equivalence if we can. I think we can do it at quite an early stage, and start to bring about this idea of balance, so that the equal sign doesn't just become a command anymore, but it becomes a useful operator. From Stuart there, I like that in the chat, just the equal sign as a balance point. That works nicely for that sort of metaphor of balance, and we'll see some of that later on. So one of the ways we can tackle this, I think, is to have a look at equations with coloured rods. So I'm just going to move now, hopefully, to the visualizer. I'm hoping that you can see that, and just produce my favourite Cuisenaire rods there. Now, if you don't have physical manipulatives, or you're unable to use them, there's obviously digital manipulatives available online, and I can share a link with you in the next slide, I think. Mathsbot.com is an excellent place to find digital manipulatives, and you can do everything plus more, to be honest, with some of the resources on Mathsbot. So what do we have here? First of all, well, Cuisenaire rods, we've got a red, and I've produced two whites, and of course with that we can see quite clearly that they are in fact the same. So we can be saying there that red is equal to two whites, and although that might seem quite advanced, I would wager that primary school pupils could very, very quickly pick up what is going on here. We've made no song and dance about using the letter R to represent the red tile. That's just what we do. We haven't had to have a guessing game about what letter should we use or what should we use for white. We just say, well, we want to use W to represent white. And in this case, we can see they're both the same size. The beauty about these manipulatives is that you can rotate them around and they're still equal. So now this actually looks a little bit different. That's red's equal to two whites, that's white's equal to two reds. It's the same thing. So what we can do is we can also write this equation like this. And what's so nice there is that we can see that equality reads both ways. We can read left to right, as we're so often used to doing, but don't forget we can read right to left. And so that's a nice little thing to build in very early on for students, is giving them this opportunity to appreciate that we can read equations in two directions. So just building on from that, let's produce some more tiles here. What do we have? So here's green and three whites. And again, what we can be doing here is asking the students to work with these tiles and then come up with the equation themselves. Can you write an equation that that represents this situation, and we would be looking for something like this. I think I'll keep the red and the whites on actually. And then we can extend this a little bit further, because we might be able to see that 2 whites here was the same as a red. And so here's 2 whites here. What might we be able to do with this? Well, since we know 2 whites is the same as a red, then maybe we could take these 2 whites out of here and replace them with a red. Just find our other whites to build that model up. But hopefully you can see that what we're doing, which really starts off very simply, is actually knocking on the door of some quite sophisticated thinking. Because now we can say, well, green was equal to 3 whites, but since 2 whites are a red, then can we now say that green is equal to a red plus a white, or a white plus a red? And of course we can. And it doesn't matter which order that's in. Red plus white, white plus red. And we're just bringing in that formal notation right at a very, very early stage. Obviously, we aren't solving anything, but we're having a good look at equality. Okay, so let's just take a couple more of these. And we can just continue to build the complexity. Now, what you could do, for example, is ask students to produce 2 greens and white, and then ask them to dig into their Cuisenaire rods and find a combination of rods that would be equal to this one. Find a combination of rods that allows you to build an equation. So this one works. You could put criteria on this. You could say, I want you to find 2 rods that completes this equation, or I want you to find 3 rods, or I want you to find 2 of the same plus a third. You can add all sorts of different constraints onto this, but then we'll be able to get ourselves to something like this. And here we just have an opportunity to keep building and keep going with these equations to create something quite complicated at quite an early stage, which I think is worth doing. It's worth spending the time allowing the students just to get to experience this. And then, of course, what's quite a nice thing to be able to do here is something like this, and perhaps realize that we can replace the 2 light greens with a dark green, for example. And then we could call that D plus W equals yellow plus red, and just carry on manipulating these, challenging students to build equations and build the most complicated equations that they can. Okay, hopefully we're back to the PowerPoint. And so, like I said, if you want to use the digital version of these manipulatives, then there's a link to Jonathan Hall's website, MathBot, where you can have all sorts of fun with that. I'm sure many of you have already used MathBot. And if you want a little bit more information on using Cuisenaire rods all the way through the school, then you can check out that ATM publication, which is Cuisenaire from early years to adults, which is great. And also, if you can seek out and find any of Caleb Gattegno's writings, in particular now Johnny Can Do Arithmetic is a great, great publication. So there's some resources if you want to know a bit more about using those coloured rods. Now, hopefully we can have a little look at this idea of balance, and you probably recognise this idea, this sort of mobile thing that hangs over a child's cot, and that's just to try and get your mind into the sort of way of thinking about these type of diagrams. So in this case, what I think it's worth explaining is that this entire system is in balance. It would be hanging from some point suspended on the ceiling, and then I'm pretty sure you can figure out that whatever mass is hanging on this arm would have to be equal to the sum of all of this stuff here. And then, of course, these two, they're in balance with this green one. So then there's a sort of balance. So there's sort of 2 equations going on here. And I suppose really it's just a a little chance for you just now to key into that chat window what's green equal to, so G equals, and then what's P purple equals, so you can just play along at home here. But what I'd like you to do is just think about the steps that the pupil's going through while they're doing this. So how are you actually taking the information that we're given, yellow is 2, and working out the values of green and the values of the purple there. So anybody that wants to play along can play along in the chat there. Well done, Sarah. I can see some of these chat window comments coming through. And then we've got equations getting built up as well, which is lovely. Well done, Stuart. Yeah, that's definitely a nice thing that we can do. Kevin as well. We could start to look and see what equations can we extract from this, which is nice. And something that you would perhaps do maybe once you'd played around with this intuitive phase. So what's actually going on here? Well, yellow's 2, so we've got 2 yellows. So this little arm must be worth 4, and it's a perfect balance with the green. So this green must also be 4. So we've already got the students just looking at this idea of thinking about the balance. And since 2 yellows is 4 and a green is 4, then that whole thing is 8. So the purple one must be 8. It's not a difficult one really, but a good one to get started with. Now, how about you have a try on this one and see what you think here. What's green, what's yellow in this case? Brilliant, I love it. The whole chat window is just full now of G equals and P equals and Y equals, which is good. So again, this shouldn't be too challenging, but the important thing is to try and think about what thought processes are going on in the student's mind here. This idea of these mobiles, we're thinking algebraically is what's happening here. We definitely are. We're looking for balance. We're looking for equivalence. We're thinking in a very algebraic way without actually doing anything formal at all. And so we could spend a lot of time on this type of thing, increasing the complexity as we go. In this case, what's actually going on? So we've got these purple things are 2 each. So this whole arm of 3 purples must be worth 6. So these 2 greens are worth 6, which means 1 green is worth 3. 1 green must be worth 3. We've got 6 over here, which balances with this yellow, which must also be 6. And I think that means 12 and 12 on each side. So hopefully that makes sense and that one works. And there might be another one for us to look at. And this is the last one. So feel free to have a go at this one if you want. Again, just thinking through what might be going through the student's mind. And we don't want to be forcing any hard and fast method. This is really where we can have a nice conversation about how did you do it? How did you see it? What steps are you taking to work this through? So we've got some nice equations coming through. Then we can also take steps to substitute into those equations if we want to. For me just now, this is really about, can we just figure out these values, and then can we verbalize what it is we've done to get these missing values? But of course, these things are extendable. You can go as far as you want with these, depending on how the class is and what the students are ready for. So quick check on this one. 3 purple ones there have the value 4 each, so that must be 12 down this arm, which means this whole section must be worth 12. And since this is in balance, each arm is worth 6. So yellows must be 3. And then since this arm is worth 6, and we said purples were 4, greens must be 2. So yellows 3 and greens 2. Well done, everybody who got that one right. Here we go then, if we can just sort of move on a little bit. I've tried here to continue this idea of the coloured dots. Now, if you have issues with using different colours, maybe different shapes, would work instead. I sort of avoided letters at the moment, but ultimately, you know, the abstract sort of notation is coming, but we're just building towards it. And now I feel we've taken this balance metaphor and sort of put it in a different context, but put it in a context that is starting to lead towards our formal written out equation. So this one should be quite simple to solve. And again, we would really just be saying to the students, well, what's a yellow? And they'll be saying, well, a yellow must be 2. How do you know a yellow is 2? Well, 3 yellows is 6, so each yellow must be a 2. We're trying to bring in this conversation about dividing here. We really do want to be sort of trying to talk about 6 dividing by 3 is 2, but there's no reason why we can't at this stage also just introduce another expression here. If we've already done it with the coloured rods, then it should be straightforward enough to produce another expression here. And then since we know that green is equal to 6, then we can just sort of elaborate that a little bit further. And now we actually do have an equation. And then if we have that conversation around how do we then know what yellow is, then what we've actually managed to do here is go from those mobiles, which are just a sort of fun and colourful entry point, to the balanced scale system here, to then a formal algebraic notation. Now, you may well want to just spend a lot of time on the scales without the formal notation, but then we can always start to add the formal notation as the confidence grows. So again, what have I done here? Really, if I flick back and forth between the slides, apart from changing the size of the fulcrum in the middle there, all I've done is switch the sides around. So the left-hand side has become the right-hand side and vice versa. And then it just gives us another chance to say there's no harm in expressing an equation like this. And then we can even leave our answer like that. And I feel some students would think that's wrong to leave an answer as 2 equals y, but what we want to encourage more and more is that idea that equality runs both ways, and if 2 equals y, then y equals 2. And so I would consciously build in an example like this so that we can have that conversation. And you can see what's happening here. We've now removed the yellow dot, and we're now looking at 3 greens is equal to 12, or 3 greens balances with 12. What do we need to do to solve this? And we can see we can build equations and work out the greens there. Just extending and extending here. Now we've got unknowns as coloured dots, but we've also got constant terms bolted on there. And it would be really interesting to give this to a student and talk to them about how they would figure out the value of a yellow without using any sort of formal method, because at this point I'm still just looking for intuition and just common sense thinking, and students actually just trying to verbalize what it is that they are doing as they try and work through these things. So in this case, I think what we would need to be appreciating is the fact that a yellow appears on both sides. That's such an important thing, and we need to have a conversation around why removing the yellow from both sides of this thing is going to help us simplify our equation. So there's a lot that we can take from this quite simple looking diagram. If we remove one of the yellows, then we want to be understanding that that's going to knock the system out of balance. We can't remove one of the yellows from one side if we don't also do the same from the other side. So there's an equation that represents this, but then there's the step that we would want to be taking here. I'm just flicking back and forward between the slides. So there's the 2 yellows on the left, and then we've removed the yellow from both sides, and we've managed to simplify this while maintaining the balance. So important just to keep emphasizing that same operation on both sides, maintaining the balance. Then we can develop the formal algebra around about it, whether we do it straight away or whether we wait until we've done lots of these scales and then we start to bring in the algebra, the formal algebra. That's absolutely fine. But what you might have noticed already with this talk that I'm giving is that pretty much as soon as I possibly can, I'm bringing in some formal abstract notation. I'm not making a big song and dance about how it's written. This is just how we write it. And so I'm trying to make these connections between the pictorial representations and the more abstract. And then, of course, there's our next step, is actually appreciating that we would subtract 2 from both sides of these scales. We would still be able to keep the balance, and we would go from yellow plus 2 is equal to 5. We would go from yellow is now equal to 3. And we could follow that through with the formal algebraic step. Okay. Again, I'm just keeping a little bit of an eye on the chat. It's great to see you all chatting away and sharing resources as well, which is brilliant. The scales work with negatives. Now, you've probably seen the kind of textbook pages with a bag, some sort of bag or 3 bags of something, and they're all labeled X, and then one's got a hole in it, and you can see that 3 things have fallen out of one of the bags. And this is the way of trying to say sort of 3x minus 3. But I feel that's starting to get a little bit contrived, and that actually, why not wait until we're comfortable with this type of setup and then introduce some negatives here. And instead of having to force the visual representation to serve our means, why don't we use the visual till it's sensible to stop and then change our representation slightly so that we can move on from that. So in this case, we would want the students to be thinking, what's the value of the purple one there? And if they wanted, they could write down an equation. What we really want to be thinking about is this idea of having to add 3 onto both sides, and obviously that brings in its own conversation. And that's where these scales are starting to get a little bit more challenging. And actually, you might have wanted to do some work with the algebra tiles before we get onto this, and we'll see the algebra tiles a little bit later in this presentation. So we could ask the students to write an equation to represent this situation. We could then talk about how can we simplify this. You know, we're adding 3 to both sides, which gives us a simpler equation. And then if 2p is equal to -2, if 2 purples are -2, and since both purples are the same thing, they must both be -1s each. And so we can simplify that thing down eventually to get to this point, all the time talking about simplifying through. So really just a summary on this idea of the scales and balances, and I'll just let you read that while I have a quick look at the chat. Yeah, lots of good stuff. Clearly the scales metaphor is something that's popular, although there is a conversation around whether a sort of traditional balance scale is even a thing that students would understand, but they tend to understand them. Digital scales aren't quite going to work the same, but definitely the strengths here to this are the fact that it's quite an intuitive method and you can deal with unknowns on both sides, and it builds a way into the formal notation. But there are limitations using this method, and it's very hard to represent sort of equations with fractions and things using this approach. So the scales and balances are strong and they're a good way in, and they link to the abstract notation, but then they do have their limitations. So then we can have a look at this idea of a number story and connecting that to function machines. So, you know, students love these, in my experience anyway. They seem to take to this with great enthusiasm, and will very, very quickly tell you the answer, especially to something as straightforward as this one. A number, when I add 7 to it, the new value is 12. So they'll very quickly tell you that number is 5. And when you ask them why that number is 5 or why the answer is 5, they'll say, well, because 7 plus 5 is 12. And while that's useful and shows there's some quick number sense and number bonds going on there, it's not really what we want, in that we're hoping to build in this idea of inverse operations at some stage. So what we don't want them doing is just trying to pluck out of thin air the number that makes this story fit. What we want them to appreciate is that there's actually a procedure or an operation that we can do to give our answer. So I think the student that says because 5 plus 7 is 12 can get the answer right, but the student that says because 12 minus 7, or the difference between 12 and 7 is 5, is the one who's starting to get the idea of inverse operations. So to help and give some support with this, we can get students to draw out a very simple function machine. Now again, I've used the letter n here to represent my number. It makes perfect sense. Why bring in x just now when n would represent number so well? Students take to that, and then we can build that function machine. And at that point, you can also say, well, what would the formal algebra look like? And there we go. We've sort of connected the number story to a function machine, to the formal algebra, which we're not going to do any more with this formal algebra just now. We've just built this little equation up. But what we would then be doing is trying to encourage students to build up these inverse function machines and try and say, well, if our number plus 7 gives me 12, can we work this backwards? And what would be going into these boxes to try and run this whole system in reverse? And then this is where we can start saying we want to do the 12 minus 5 operation, sorry, 12 minus 7 operation to get our answer of 5. And The reality is that students can be quite impatient with this because they can see the answer. And so it's really important that we communicate to them that it's not just about the answer, and that we're really thinking about a stage to our working. How do we actually step through this? And the way to get to that is to add more and more complexity. So here we go again. You know, I'm sure students would be able to answer this without doing anything written down. Plenty of students will be able to get to the answer to this. And actually, that's great. That's absolutely fine, because they're starting to see the bigger picture here. But there are still plenty of students who would like to see the thing, the story written as a function machine, and then there's a perfect opportunity here to give the formal algebraic notation that goes with it, and then we would just turn this function machine around. And we've added an extra step here, but the beauty about solving equations is that we can tackle a very, very complicated and difficult situation by breaking it down into small, simple steps. So there is no single step in many equations that's actually difficult, but it's the combination and the order and the structure of those steps that is where the challenge comes. So here we go again. A number here which I multiply by 3, divide the result by 4, subtract 1 from this result, the new value is 5. I think we're starting to get to the point where some students might be thinking, oh, this is giving me a sore head, actually trying to do all this. A lot of them will try and do it all in their head. And then it's a little opportunity for us to educate them in the fact that showing some working is actually not a bad thing to do. And so even if that working becomes a function machine like this one, and then an inverse function machine, then that's fine. But what's really interesting here is that algebraic expression, that equation that we can actually build up here. And don't be afraid to show students something like that. This is a complicated looking equation that comes from a multi-step number story, but it really is just building on from what we did in the previous examples. And so then when we start to run these in reverse, I've known classes where they just love a reverse function machine. They'll just start processing everything through it because they've realized that I can break this down step by step. Now, I just want to focus on this just a little bit more, because what it is possible to do is start to go the other way and start to give students an expression like this. So don't give them the number story, don't give them the function machine, give them the equation like this one here, and ask them to tell you the number story. So if we can see this equation here, we want them to look at this and say, okay, so there's a number, I'm multiplying it by 3, I'm dividing it by 4, I'm subtracting 1, and my final answer is 5. And so it's so important to try and think about doing this. I think, as Michael said there, it lends itself to changing the subject so well, because changing the subject of a formula is nothing more than solving an equation where, in many cases, all the number terms have been replaced with letters. So changing the subject and solving equations is the same thing, by and large. So if you give an equation like this, ask the students to tell you the number story. Give them a function machine. Ask them to tell you the story. Ask them to make the equation. Even better than that, give them the equation and ask them to tell you what all the steps are in order. So multiply by 3, divide by 4, subtract 1. Then say to them, what are we going to have to do to undo this? Don't draw an inverse or reverse function machine. Just tell me what are the steps we'll do to undo this. So first of all, we multiply by 3, then we divide by 4, then we subtract 1. How do we undo that? Oh, well, we'll have to add 1, then we'll have to multiply by 4, then we'll have to divide by 3. And that's a glorious moment, because what they've done there is, before they've put pen to paper, they've built up a conceptual model of the entire solution by reversing each operation, or by doing the inverse of each operation in the reverse order. And I've spent entire lessons just doing nothing but that. Tell me what the number story is, tell me how we're going to undo it. And I think it really builds students' confidence. Now, we've got another one here. Why have we got this one here? I think it's the same one, or is it more complicated? Yeah, again, the thing here is that we can just keep building and building the complexity. You can make some incredibly complicated equations from this idea of a number story, and then you can solve them using the inverse function machine. And ultimately, you want students to be able to tell you each of the steps in this inverse function machine without actually writing it down, because then you've built up a solution set for this type of equation. So here was one that we actually saw earlier on, one of the simpler ones. There's the equation that went with it, but only now what I'm going to introduce in addition to this inverse function machine is actually, well, how do we solve it abstractly? How do we actually write this using formal notation? So here's this idea of subtracting 7. Where's that come from? Well, here it is here, obviously. And then what's so important is that 13 minus 7 is 6. Now, there's no 6 appearing here, but there's always been a 6, just sort of at this intermediate stage, just before we move to divide by 3. So where does that 6 appear? Well, obviously, that's now going to be what's left once we've subtracted 7. And then what was our last step? It's divide by 3 over to the formal algebraic notation here. What's our last step? It's divide both sides by 3. And there we have our final answer. So now we've taken a number story into a function machine, reversed that function machine using inverse operations, and written out the formal algebraic notation, gone through the steps and tried to connect it all together. I think that is a powerful thing to be able to do. So I'm going to have to stop there on the number stories because I still want to squeeze in a little bit more if we can on the algebra tiles. The strengths here for the number stories and function machines, again, it's quite intuitive. It connects up to the other representations we've looked at. It brings in the inverse operations. Also, it's good for changing the subject of the formula. And it's another entry point for formal abstract notation. But you know, I have to say, yet again, it's a representation or a metaphor that becomes a bit contrived for some equations. So something like 3 minus x. Now, what would you say here? I've thought of a number. I'm subtracting it from 3 and the answer is 8, maybe. Or would you actually say, I have a number, I've multiplied it by -1, I'm adding 3 and the answer is 8. So you start getting into sort of complex language around what this equation what is actually happening here. For me, this is actually a number multiplied by -1 with 3 added to it. But then that's not what the students will see. So I would then suggest maybe we leave this type of problem to go on and explore that in a different type of representation. And then the big limitation of function machines for me is this idea of unknowns on both sides. You could contrive something and say, I'm thinking of a number, I double it, I add 3, and then that turns out to be equal to my number minus 4 or whatever. And then you can contrive it, but it starts to become unnecessarily complicated. So I would stop there and maybe move on to some other type of representation. So what's important just now is that we check what time it is, so we know if we've got enough time to go any further. I think we've got enough time to maybe have a quick glance at some algebra tiles. If not, then please let me know. Just very, very quickly on the algebra tiles. So you've maybe seen these before. I hope you have. You can get the physical ones, or you can use Johnny's digital ones on Mathspot. And so here's how we would set up x plus 2 equals 5. Very, very simple setup here. And it kind of links into the coloured dots that we've been using before. There's x plus 2 equal to 5, not 6. And then we can build our equation like this. Now, how would we try and solve this? Well, we would subtract 2 from either side, and we can do that just like this, very clearly showing that we're physically removing 2 from here. Now, if you're a fan of 0 pairs, you might be talking about adding -2 to both sides of this thing, although I would tend not to in this case. But if you add -2 to both sides of this, then you create 0 pairs that will cancel away and will still lead the same answer. But a discussion around that is perhaps for another time. And we can see there that we've got x equals 3. It's just the other one I wanted to show you quite quickly was here's 2x plus 4, and here is 5x minus 2. So for me, sometimes I would talk to students about having the largest x values on the left-hand side. And that's really just personal style of mine, because of course we could solve this anyway. But the beauty about this is that you can just do that, and suddenly you've got your x values on the other side. You subtract 2x from both sides, and then we just need to think about how we would finish this. And the way to deal with this is to add 2 onto here, which would give us 2 0 pairs, and add 2 onto here, which then these would disappear. And what we're left with will be 3x is 6. And when you have 3x equals 6, just do an actual physical division to see that each x corresponds with 2. Now, I think that we might be nearing the end, so I'm going to just switch to the final slide, which is this one. Hopefully you can still see that. And I am still here. If anybody has any last minute sort of questions or anything that they wanted to say, you're more